Chapter 4 in your textbook. You should have completed the homework by this time. Projectile motion is two-dimensional kinematics. That's how we're going to look at it at this point. Even if you include 3 dimensions, you can usually break up, when you throw an object, you can break it up in a two-dimensional plane. And we're going to do that at this moment. So motion in 2 dimensions. I want to talk about the basic equations. I want to talk about zero launch angle, general launch angle, and some key characteristics of projectile motion. So in two-dimensional kinematics, we will break up the motion into its horizontal and vertical components. So you want to think of it this way. You want to think of it as motion in one direction, usually the horizontal, as motion under constant velocity. And perpendicular to that is motion under uniform or constant acceleration. So in one direction, the horizontal direction typically, is the motion of the constant velocity, where it goes steady, 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 assuming there's no air friction or any outside influences, any outside forces. And in the vertical direction, if we're looking at just motion affected by gravity, free fall motion, we would have uniform acceleration in the vertical direction. Gravity is always pulling downward. It doesn't go on a holiday because you're moving. So if we look at the motion of an object in the horizontal direction, and we look at the motion of an object in the vertical direction, and we compare those, we find that one is completely independent of the other. And that's what it's saying here. The motion of an object in the horizontal direction is completely independent of the motion in the vertical direction. The one thing they share in common is the time. You can, when you use these equations, you'll find they have the same time unit. All right, so here is a picture of a device that you can push at a constant velocity horizontally, and there's a spring-loaded projectile that is shot straight up, and as it moves horizontally, the projectile stays right above the device, and so when it comes down, it will land back into the device. This is a nice little demonstration. And it's emphasizing the motion of an object in the horizontal direction is completely independent of the motion in the vertical direction. Even though this object, assuming there's no air resistance or anything like that, it's horizontally moving steady, 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 but it's vertically accelerating downward. It slows down on the way up, and it speeds up on the way down. But it stays over the object because both the object and the projectile have the same horizontal velocity. Here's another example. You have an individual on a skateboard. They're moving steady, 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 and they drop it looks like a basketball. The basketball will stay underneath the person's hands as the person moves forward, as long as they're moving forward at a steady, constant, speed in the same direction. The ball accelerates downward. And notice if you follow the path of the ball, it looks like a parabola here. So uniform acceleration in the vertical and constant velocity in the horizontal. Here is a vector diagram of this is a initial velocity vector, and this is the launch angle. You can actually write equations in projectile motion for general launch angle, where all you need is the initial velocity of the projectile and its launch angle, and you can make predictions about the range, how far away the projectile will land, the maximum height, things like that. Now you can break up any vector into its horizontal and vertical components. So notice I've taken this vector, I figured out the horizontal component, which we call V or Vox, V initial in the x direction, equals the initial velocity, the magnitude of the initial velocity times the cosine of theta. And then to get the initial velocity in the y direction, V sub 0 y or V naught y, we take the initial magnitude of the initial velocity and we multiply by the sine of theta. So we break up or we decompose the initial velocity vector the total velocity, into its x and y components. And we treat each motion separately and then combine the results. The one thing, as I said earlier, that stays the same for each type of motion is the time. So we're going to treat two-dimensional kinematics, two-dimensional motion, as separately as one-dimensional motion, just in the x direction, and one-dimensional motion in the y direction, and then we combine the results. So here's a handy-dandy formula that we'll derive later to give you the range. And if we launch a projectile at an initial velocity v0 at a launch angle, if you know that initial velocity and you know the launch angle, you can calculate the maximum range. And you can think to yourself, what must theta be for this range to be maximum? Now, this is an ideal case where there's no air resistance, no wind. It's just gravity alone that's pulling it down. Well, the maximum range, if you put in 45 degrees here, 2 times 45 is 90. What's the sine of 90? Isn't the sine of 90 degrees 1? So that's when this maxes out. So the max would be v0 squared over g. That's only if there's no air resistance, an ideal case. Also, there's a lot of symmetry to projectile motion. Here is a graph of that symmetry. On the way up, you see the velocity is shrinking. And then when you get to the top, the only velocity at the top is the horizontal component of the velocity. So v initial x, which you figured out here, will equal vx here. And v initial y decreases to 0 at the top. And then on the way down, you can see the symmetry here. Here we have a positive angle, but over here we have the negative of that angle. Here we have a positive angle. Over here we have the negative of that angle. But notice at the very top, the velocity in the y at the time it's at the top will be 0. You want to remember that. But the velocity in the x at the time it's at the top will equal the initial velocity in the x, which you figured out when it began, because this stays constant throughout the motion, that horizontal component. The acceleration in the y will always be negative g if we're near the surface of the Earth and we are in free fall. We can neglect air resistance, or we're dealing with projectiles that are not affected by air resistance. It's negligible. They're at low speeds. You are aware if the speeds increase when you do have air resistance, it increases dramatically with increasing speed. Now, we could also talk about the time intervals here, but what you should see is how the angle from corresponding sides are on the way up and on the way down, how one's positive and one is negative, but they are equal in magnitude. So, uniform acceleration perpendicular to constant velocity. Now, there's other ways to create this situation. It doesn't have to be about gravity. We could talk about the motion of a charged particle like an electron in an electric and magnetic field, and we could create similar situations where we have acceleration, uniform acceleration in one direction and constant velocity in another direction. In fact, there's a homework problem that does that. All right, here is another graph of the motion of a projectile. If we take a projectile and let's say there was a table here and we had a ball roll off the end of a table, then you would see it. This could be the edge of the table, then it would fall such that after a certain amount of time it would be here, and then another amount of time it would be here, another amount of time it would be here, and so on. And it followed this parabolic path here. But you should notice something about this. Notice how it's showing it's accelerating on the way down. Can you see how the distance between here and here is increasing, as time proceeds? We can call this zero launch angle. Imagine a ball or something rolling off the edge of a table and then falling. The initial angle is 0. let's look at this. Now, if you look at the horizontal motion of the same picture, notice it's steady, steady, steady in the horizontal. This is a motion diagram. And we could represent the object as by its center of mass if it wasn't shaped like a sphere or a ball. And here's the vertical motion. Notice that this is showing acceleration. These dots represent equal time intervals. These dots represent, in the spacing here, equal time intervals. So steady, 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 steady horizontally, that's constant velocity. And here it's increasing, which each passage of time, each unit of time. So it's speeding up. Gravity is accelerating it downward. So the vertical motion is accelerated. The object goes farther in each successive interval. This is a great picture to look at. Now, if there was no gravity, it should just continue on in a straight line. Steady, steady, steady. But since there is gravity, as it's moving steady, steady, steady horizontally, it's also falling. It's also in free fall vertically. But we can treat each one of these motions separately and then combine them. So for the equations of motion for the vertical, we're going to use the Fab 5 equations. And for the horizontal, we just have one equation. All right, here is a golfer, and you can see the golf ball. It rises and then it falls. If you notice, because as it gets towards the top of the trajectory, the ball is slowing down to zero, a velocity of zero. It's where it's changing direction at the top, so its speed at the top is zero. Since it's slowing down towards the top of the trajectory and then speeding up the other way, it actually spends, if you cut this trajectory in half, it actually spends about 71% of its time in the upper half of the trajectory. We call that hang time. And you can actually exploit this. You see this in sports. You see this in dancing, where professional dancers will jump and they'll do this parabolic motion. And it'll appear like they're defying gravity as if they're floating. But what's really going on is they're slowing down in the upper half of their trajectory. So they technically are spending more time in this region of the path. So I have a problem where you can work this out to actually show you are actually spending about 71% of your time in the upper half. All right, here is a baseball pitcher throwing a ball, or this could be first base, and this could be the pitcher, or this could be a shortstop. This could be second base. But the ball, if you were to throw it and there was no gravity, it should go right straight across to A. But since there is gravity, it'll still go steady, 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 steady across the page here, but it'll fall. So it'll follow this parabolic path. To figure out the distance it will go from the throw to A, you'd simply use the horizontal distance traveled formula here. Change in x. Remember, change in x equals v average times time. But the velocity in the x direction, v naught x, or vox, is constant. So it's like speed times time. That would equal distance. You could simplify the formula to x equals v naught x, the initial velocity in the x direction, times the time. So there's your one equation. However, in the vertical, the distance between A and B, you would use the world line equation for that. And initially, it's in the vertical, it's at rest, and then it accelerates downward. So its initial position is 0, and its initial velocity is 0. So it's only the acceleration term in that world line equation you have to worry about. Remember, for the acceleration in the y, you would replace it with the acceleration due to gravity, g. So we have change in y equals 1/2 gt squared. That's the vertical drop from A to B. So, to sum this up, the motion in the horizontal and the vertical directions under the influence of gravity are independent. We'll solve the horizontal using the principle of constant velocity, and we'll solve the vertical using the principle of constant acceleration. And here is a example of someone jumping, just straight down from a high point and jumping out. You could be asked the question, what is the final velocity? Which one has a greater final velocity? Well, the final velocity for the one that goes straight down, if they start from rest, and we knew the height of this cliff, we could use that formula v equals the square root of 2gh to get v sub y here, right before this person hits the water. Compare this final velocity to this final velocity. Which one's bigger? Did you guess number 2? Yes, because number 2 not only has the vy, but it's a vector addition of vy and this initial velocity in the x direction, which stays constant on the way down. When you add these two vectors, and remember these are the legs of a right triangle, and this would be the hypotenuse. Isn't the hypotenuse the longest side? Yes, the hypotenuse will be longer than vy, one of the legs, because you're adding this other leg. So yes, this will have a greater magnitude. So the speed here will be greater than here. The one difference is the direction. Notice these velocities are different in direction. They're different in magnitude, which is the speed, and they're different in direction. So this person will hit with a greater speed. And it's at this angle here with the horizontal. Here's an interesting problem. The landing speed of these two snowballs, they're both thrown with an initial velocity at different angles here. One is thrown 40 degrees above the horizontal, one's thrown 40 degrees below the horizontal. And what's interesting is when you figure out the landing speed of the two snowballs, you find out that the landing speeds are, guess what? The same. So for a given initial speed, the speed of the landing does not depend on the direction of throw. That's sort of interesting. One of the homework problems, it's the snowball problem, you're actually asked to show that this is true. Later on, we'll do this in a simpler way. We'll talk about energy. We'll talk about potential and kinetic energy and how it's an easier problem to solve to get the final speed if you think in terms of energy before equals energy after, even though you see a lot of changes going on. We'll talk about conservation of energy and do this problem again later on. You should try this problem in your book to prove this to yourself, that the speeds would be the same regardless of this launch angle. Now, one is in the air for a longer amount of time. The one that's thrown up will be in the air for a longer amount of time, but the final speed at the bottom will be the same. Do you know why? This is answered in your book in one of the conceptual questions. Go read that. All right, so here's the equations we're interested in. We'll have the equation for the x position as a function of time, and also for the y position as a function of time. Notice this one is when, this is your change in x equals v average times time, just rewritten, but this is when the velocity is constant. Your final position will equal your initial position plus what changes it. It's having initial velocity over time is what's changing it. And then you have your world line here for the y position. So your final vertical position, some later time, will equal your initial vertical position plus your initial vertical velocity times the time minus 1/2 gt squared. Now we're making up positive, so down will be negative. And of course, you can use the other equations in your arsenal of motion under uniform acceleration. But you only need one for the horizontal. So if we took these formulas and we combined them and we eliminated time, we would get a parabolic equation with y as a function of x squared. You could do this as an activity. This is a little challenging. You have to bring in your trig relationships, but you will get a parabolic relationship. And this is very common, this parabolic path. We're going to find out later that this is really just a very good approximation to projectile motion. When we study gravity and satellite motion, we'll find out that this really is part of an ellipse, an elliptical motion, and it leads to the idea of satellite motion. So projectile motion is really a special case of satellite motion or elliptical motion, and we'll talk about that later. But for all intents and purposes, we're going to express this as a quadratic, as parabolic motion, just like the world line suggests. All right, here are some equations that are in your book for motion in the x and y directions. We'll treat them separately. We have position as a function time for x and y. We could use the world line for both, but for the position as function time in the horizontal, remember the acceleration in the x is 0, so this term cancels out. So you just have x equals x naught plus v naught xt. This term cancels out. However, in the y, you'll have to deal with all three terms, including the acceleration term. So in the x, you would get rid of the acceleration term, and that would be your three equations. In the y, you would keep the acceleration term. So you could put an x through this, this, and this, if in the x, the velocity is constant. It's the same equations, though, just missing a term. All right, here are some assumptions we're going to make. We're going to ignore air resistance. We're going to treat g as 9.81 meters per second squared downward. We're also going to ignore the Earth's rotation. We're not technically in an inertial reference frame because the Earth is accelerating, but we are going to treat it that way. And we're going to let the y-axis represent the vertical, and we're going to make positive upward and downward negative in general. So g will be negative. And this is what I mean. If you drop a ball, the x acceleration is 0, the y acceleration is negative g. If you throw it, it's the same case. It's still accelerating at 0 in the x direction and negative g in the y direction. So the acceleration is independent of the direction of the velocity. And here is those formulas again. And notice now we've dropped, for the x, we dropped the acceleration term because there is no acceleration. So here's this formula. This is just saying the velocity in the x direction stays constant. The initial velocity in the x direction will equal the final at some later time, including at the top. And this is just saying the same thing, but it's showing what equation we're using here. So we got the world line for the y. It is quadratic. Here's that v equals v naught plus at rewritten. And here's that time-independent equation. It's all the same as chapter 2 for when you're dealing with the vertical motion. So here are some questions that you would be asked. If you throw a stone horizontally at a speed of 5 meters per second from the top of a cliff that is 78.4 miles high, how long does it take for the stone to reach the bottom of the cliff? How far from the base of the cliff does the stone hit the ground? What are the horizontal and vertical components of the stone's velocity just before it hits the ground? Well, this is a great problem to solve. Let's go about it. Here's a picture. This is a zero launch angle problem. Here's the initial velocity. It's going to fall this distance, but it's going to be projected out. So the way we would solve this is we could think of it as a free fall problem in this direction. It's going to fall 78.4 meters. Its initial velocity in the y direction is 0, and its initial velocity in the y direction I'd write this way, and then I'd figure out its displacement. It has no initial velocity, so this term would go away. Now I just have the second term, but I'd make sure the acceleration was negative g. So if we put in the terms, it's just this final term here, change in y equals minus 1/2 gt squared. We'd solve this for the time, and this is the free fall time, how long it will take it to fall. Plug in the numbers, 2 times the height divided by g. Now if I made the height negative here, g is negative, so you'd still get a positive square root. It comes out to be 4 seconds. Look at the picture again. The range here is just, actually we'll just call it x. The initial velocity in the x direction shouldn't change. It should be 5 meters on the whole trip down. So we'll just use that one equation it's like distance equals speed times time. So the range here, x, will be the initial velocity in x direction times the time. We know the time is 4 seconds. The time it takes to fall will be the same time it takes to go horizontally this way. So we put in 4 seconds times 5, we get 20 meters. So the range would be 20 meters, constant velocity. So here's a picture of that graphically with the vectors. This stays steady, steady, steady. This increased from 0 to this value. And then to figure out V total, we'll use the Pythagorean theorem. Or we could, well, we're not going to use the general law of angles just yet. So here is our formulas that we can use for velocity in this direction, the y direction. We could use V equals V naught plus AT, but remember A is G, initial velocity is 0 in the y, so its final speed before it hits would be its acceleration times the time. Time is 4 seconds, so it should be 39 meters per second. The speed, its direction is negative because it's downward. So we got 5 here, and we have 39 here. How would we find V total? Again, we could use the Pythagorean theorem. We'd square the 5, we'd square the 39, we'd add them and take the square root, and then we'd get V total. I didn't do that here, but what's interesting, the longer this falls, the steeper this angle gets here, and this vertical velocity will overwhelm the horizontal velocity. It'll never quite be straight down though if it has a little horizontal component. But the longer it's in free fall, this angle, this path becomes steeper and steeper and steeper. All right, I think we'll try one more. Here's one. An assembly plant worker makes wooden giraffes. At the end of the line, the giraffes go horizontally off the edge of the conveyor belt and fall into a box below. If the box is 0.6 meters below the level of the conveyor belt and 0.4 meters away from it, what must be the horizontal velocity of the giraffes as they leave the conveyor belt? Well, let's look at this. Here's the setup again, very similar to the last problem. If we simplify it into our x and y coordinate system here, here's that horizontal distance, here's the vertical distance. I want to find the initial velocity here. Well, the horizontal equation is x equals v naught xt, and the vertical, remember it's going to start vertically and at rest, and then speed up vertically. We just have to use that acceleration term, 1/2 gt squared. We can find the free fall time by using the square root of 2gh from this. And we could plug that into here, into the x equation, because the times are the same. And that x position, we equal the initial velocity in the x direction times time. And from this, we can solve for the initial velocity here, which is just the initial velocity in the x direction. It doesn't have any velocity in the y direction. So the horizontal distance covered will be x equals v naught x times the square root of 2h over g. This is a very important relationship, step 3 here. So let's plug that in. Let's plug the numbers in. We have for the horizontal range 0.4 meters. The height is 0.6 meters. We do the numbers here, and it comes out to be 1.1 meters per second. That's the initial velocity in the x direction. All right, here's one for you to try. Why don't you try this one? It's ice cream parlor stand slides a complete ice cream sundae down a counter at a constant speed of 2.0 meters per second to the server. If the server catches a sundae 7 centimeters from the edge of the counter, how far do they fall from the edge of the counter to the point at which the server catches them? Can you figure this out? And I think this is where I'll stop the video.